Hey chemistry aficionados, we are doing simple gas law problems. This is a review worksheet. You can find this worksheet in the description. You can click on the link and then you can also find the key for the worksheet. Let's get going. Okay, can of spray paint contains nitrogen gas, the propellant. Pressure of the gas is 3.5 atmospheres. When the temperature is 20 C, what is the pressure when it's 50 C? Okay. Now, before we do any of these problems, it's probably good to kind of remember our simple gas laws here. So let's think about it here. So pressure is proportional with temperature, right? So that means that if we have the pressure and temperature in one set of conditions, it has to be equal to pressure divided by temperature in a second set of conditions, okay? All right, so what do we got? We got P1. We've got T1. It looks like we've got T2. The only question is, what is P2? Okay. Now, the only thing we have to do before we put our numbers into our equation is we got to make sure that we're dealing with Kelvin. Celsius, degrees Celsius is no good. You want degrees Kelvin. Okay, so let's go ahead and do that real quick. Remember, to figure out what Kelvin is, it's 273 plus whatever your degrees are in Celsius. So for T1, that's going to equal 273 plus 20. That's 293. And for T2, that's going to equal 273 plus 50, or 323. Now we're ready to plug and chug. So we are trying to figure out what P2 is. We'll rewrite this as P2, P1, T2 over T1. And then we just plug in, right? So P1 is 3.5 atmospheres. T2 is 323 Kelvin, and T1 is 293 Kelvin. Notice that the Kelvins are going to cancel out. Do the calculation real quick, and we get a pressure of 3.9 atmospheres. Remember, just keep the same units. When in doubt, keep the same units as you start with. So we're in atmospheres. Okay, question number 2. Looks like we're dealing with a volume. 90 mils of volume of helium gas was collected under pressure. This is our V1. This is our P1. What we're looking for is V2, and then our pressure would be P2. Now let's remember our relationship here. Pressure, as you'll remember it, is inversely proportional to volume. What does that mean? Well, it means that if you have pressure times volume in one set of conditions, it's equal to the pressure times volume in a second set of conditions. Now let's go ahead and solve it. We are looking for V2. So just rewrite this. V2 equals P1 times V1 over P2. P1 being 740 millimeters of mercury. V1 being 90 milliliters. And then P2, what's it going to be if we reduce the pressure to 700 millimeters of mercury? Quick calculation gives us a volume of 95.1 milliliters. And then I always like to kind of stop and make sure that this makes sense, right? Pressure is inversely proportional to volume. So if we have a volume of 90 and we decrease the pressure, the volume should increase, and that it indeed has increased. We've got a pressure or a volume of 95.1. Okay, next question. Small bubble rises from the bottom of a lake where the temperature is 8 degrees C and the pressure is 6.4 atmospheres. Rises to the surface where the temperature is 25 degrees C and 1 atmosphere of pressure. Calculate the final volume of the bubble if its initial volume was 2.1 milliliters. Well, let's figure out what gas law we're dealing with. Looks like we've got temperature. Okay, remember that temperature is proportional to pressure. Okay, and we've also got volume. Remember that volume is inversely proportional to pressure. Well, if we rewrite this, we get this: P1 times V1 over T1. Pressure times volume over temperature in one set of circumstances is going to give us the same in a second set of circumstances if we put them P and V over T. Now we're looking for the final volume, so let's call that V2. I'm going to go ahead and just isolate V2 here. So we've got T2 times P1 times V1 over P2 times T1. Okay, let's go ahead and plug in. T2 looks like 25 degrees C. Remember, we can't use Celsius. Celsius is a big no-no. We've got to convert to Kelvin. Well, T2 in Kelvin is 25 plus 273. Remember that magic 273 number. We're looking at 298 Kelvin. That is T2. Let's do this real quick for T1. We got 8 degrees C plus 273. That's going to be equal to 281. And that was our T1. Okay, so now we can plug it in. Let's move down here and get a little bit more space here. So T2 is 298K times P1. Okay, here's our P1, the first pressure that they give us, times V1. Initially, it's 2.1 milliliters. Put that all over the second pressure, which is going to be 1 atmosphere. And T1, which is 8C, that's 281 K. Now let's cancel out. K's are going to cancel. Atmospheres are going to cancel. And what we're going to be left with is milliliters, which makes sense because we're trying to find volume. Quick calculation, we get 14 milliliters. That's how big the bubble is at the top, at the surface. Number 4, 3 gases mixed in a 1 liter container. The partial pressures are this, that, and that. What is the pressure of the mixture of gases? Now remember that the total pressure of a system is equal to the sum of the pressures, each of the individual gases. So in this case, we're talking about CO2, we're talking about N2, and we're talking about helium. Oops. Okay. Now we just plug it in. So if carbon dioxide is 250 millimeters of mercury, and nitrogen is 375 millimeters, and helium is 125 millimeters of mercury. What's the pressure of the mixture? Well, you just simply add them up. So let's see if I can do this in my head. 375 plus 125, that is 500. So in the end, we've got a total pressure of 750 millimeters of mercury. What are the percentages by moles of the gases in the above mixture? Well, let's see if we can figure this out here. We know that we've got a 1 liter container. Okay. Our pressure is 250 millimeters of mercury here. Well, we know that each gas takes up the same amount of space independent of what type of gas it is. So if 750 is equal to 100% of all the gas in the container, if we're talking about CO2, CO2 is 250 millimeters of mercury over 750 millimeters of mercury, and we multiply that by 100%, we're going to get 33% of the gas in the container is CO2. Next one, if we have, for nitrogen, 375 millimeters of mercury over the total 750, multiply that by 100%, 375 is half of 750, we're talking 50% nitrogen. And then last but not least, we've got helium. Well, if we've got 100% total, we subtract out the 33%, that's the carbon dioxide, and we subtract out the 50%, that's the nitrogen, we should get 17% helium. Okay, number 6. Atmosphere is a mixture of gases. What is the partial pressure of each gas at standard pressure? Okay, remember, standard pressure is equal to 760 millimeters of mercury. So if that's our base, let's figure this out. Well, if nitrogen is 79%, let's turn that into a decimal and multiply it by the total 100% of our total pressure. Quick calculation gets us 600 millimeters of mercury of nitrogen. All right, let's take our oxygen. So that's nitrogen. 20%, that's equal to 0.20 of our total. Quick calculation gets us 152 millimeters of mercury of oxygen. And then we got 1% is argon, 0.01 times 760. I can do this without a calculator. 0.01, we're talking 7.6 or 8 millimeters of mercury due to the argon. So there you go. These are all the partial pressures. N2, O2, argon. Okay, a mixture of helium and oxygen gas is used by deep sea divers if the pressure of the gas in the diver inhales is 8 atmospheres. What pressure of the mixture should be O2? The partial pressure is the same as what the diver would ordinarily breathe at sea level. So, partial pressure of oxygen at sea level, remember we're about 20% oxygen times 760, right? We just figured that out in the last problem. Let's just go back and take a look. We're talking 152 millimeters of mercury of oxygen, okay? What percent of the mixture should be O2 if the partial pressure is the same as what the diver would ordinarily breathe at sea level? Well, we're talking about atmospheres here. Let's go ahead and turn this into atmospheres. We can do that by multiplying by a conversion factor, right? It just so happens that 1 atmosphere is equal to 760 millimeters of mercury. Quick calculation gets us 0.2 atmospheres. Something tells me I should have known that. Okay, now if we've got 8 atmospheres of total pressure, what percent of that is oxygen? Well, if we put this over the 8, let's multiply that by 100 to get to a percentage. Okay, we're talking about a mixture that's 2.5% oxygen as the deep sea diver inhales. Okay, next up, we're getting a little bit more complicated here. Found the density of carbon dioxide gas. You collected the gas by displacing water in a bottle. The gas you collected was a mixture of CO2 and H2O. On the day of the lab, the room pressure was 730 and the partial pressure of water was 21. What would be the partial pressure of the carbon dioxide gas? Well, we need our partial pressure equation here, right? We're talking the total pressure was the pressure due to the carbon dioxide plus the pressure due to the water, right? If the total pressure was 730, we don't know what the pressure of the carbon dioxide is, but we do know that the pressure due to the water was 21. So the pressure to carbon dioxide would equal 730 minus 21 would be 709 millimeters of mercury. What fraction of the mixture was CO2? Well, let's just take 709, put it over 730, multiply it by 100%, and we're talking 97% CO2 in that mix. Last up, we got a reaction, zinc hydrochloric acid, collect the hydrogen. We've got some water pressure, we've got a total pressure, partial pressure of the hydrogen gas. The volume at this pressure was 25 mils. What would the volume of the hydrogen gas alone at standard temperature? Well, let's figure out the partial pressure of hydrogen first. P tot equals pressure due to hydrogen, pressure due to water, right? If we've got 735, hydrogen we don't know, water we do know is 22. The partial pressure of hydrogen is going to be 713, if I'm not mistaken. If the volume was 25 mils, what would be the volume of the hydrogen gas alone at standard temperature or standard pressure? Well, let's so standard pressure is 760. Okay. Let's figure out what the volume is at 735 first. So 713, okay, is to, well, I think we should probably just do the 760. 713 is to 760 as X is to 25 mils. We just set up a ratio there. Looks like our volume just due to the H2 gas would be 23.5 milliliters. Okay, and these are all of our gas problems. Thanks a lot.